cartons.
That lends a lot of credibility. You know, if you come in and can be upfront and honest and say, you know, actually in this application, I think this product over here that I don't represent would be better for you. That all of a sudden now you become a trusted advisor rather than a salesman.
And, you know, I often say that we have all the requirements of space, right? Because it has to go underground and send us data from miles and miles away, and it has to work. Like, failure is not an option.
We'll put on, you know, a standard mule shoe. Ours is slightly different just for that, but it's, you know, everybody's got one.
The top drive and the drawworks really don't care whether the electrons coming at it are from a joystick or a PLC.
The panel, what you see here on the left, which is now controlled by one of my students, is showing you actually the control of our brakes.
As of now, geothermal is a pretty small market.
If you have tortuosity, the casing will be up against the side on part of the well. There won't be any cement there. The cement will have crescent around it.
So managed pressure drilling, it's been defined as a process to precisely control the pressure profile in the wellbore.
The key is being transparent with our clients in this case. So tell them what happened. If we had a failure, tell them exactly what happened. Whether it's our fault, whether it's whatever the issue was, we need to be transparent.
I think it's very important for everyone in the industry to know what's out there and kind of what's happening downhole as well.
I've probably worked on over 40 different performance limiters in my career. If I miss any of those and the computer is raising weight on bit and I miss any of those, I have a train wreck. The computer's going in the ocean.
Here's your new colors, here's your new thing. We don't do that
at all. Here's the tattoo you need to get.
Yeah, here's the tattoo. Sorry about the last one. We used to fake that all the time.
Hello, everyone, and welcome to the Vidor Locksmith Show. I'm your host, David Gibson, and I am super excited about today's show just because we've been doing about a million things behind the scenes today to be able to get today's show launched. Like I said, this is the Vidor Locksmith Show where we are unlocking secrets to success in the oil and gas industry. One interview, one technical presentation, and one technical screw up at a time. So I guarantee you we're going to have some fun technical things to overcome today, but I'm 100% certain we can knock this out of the park. This is going to be an absolutely amazing show. We've got an absolutely amazing guest for everybody. So please do all of the normal stuff. Please like, share, subscribe, and most importantly, let us know where you're watching from. We'd love to be able to give everybody a shout out here on the screen as everybody starts to kind of like pile in. I haven't quite seen, I don't know if we've got too many comments coming in. Yeah, there we go. All right, so far we've got Abdullah watching it from Cairo, Egypt. Thank you for being here. And then Mr. John DeWart tuning in from Colorado's. I'm guessing it's Colorado Springs. I think that's where he says he's watched from. Anyways, I know he's in Colorado. Please keep Graham on his toes this morning. I'm 100% sure we will keep him on his toes. He's got me on my toes definitely so far this morning. Who else we got tuning in? Enrique tuning in from Peru. All right. Uh-oh. We got volume going in the background. Edgar tuning in from UIO. What's UI? I don't know what UIO is. Let's see. Also, we've got Francis tuning in from Katie. Graham Lawton from Alberta. Graham, thanks for being here. Kate Jackson. Good morning from the office next door. He's literally like right there on the other side of the wall. So thanks for being here, brother, for support. I don't know who this guy is. Who's that guy?
I really don't know.
I don't know who that is.
Your buddy.
Yeah, Knee's absolutely amazing guy. So thank you so much for being here. Tuning in from Tom Ball. Next one we've got tuning in from Algeria. That's Munir, I think. Yeah. Peach, second week in a row. Peach Holtzman's tuning in. You know who Peach is, right?
Yeah.
Yeah. All right. Johnny Corca tuning in from Netherlands. If you guys have not seen, Johnny has been putting out some absolutely amazing stuff on LinkedIn in regards to wellbore tortuosity and some Python script coding and stuff that he's been able to do. It's really, really cool stuff. Be sure to go and check it out. Next, we've got Alistair. Alistair tuned in from Oklahoma City, part of the Gumbo Data guys. Absolutely amazing company. Enzu from Kazakhstan. Wow, we've got a really international show. Juan tuned in from Ghana. Hey, there we go. Greg Deaton. I'm gonna have to just like run through these pretty quick. Greg Deaton. Then we've got Dexter tuned in from the Philippines. Then we've got, there we go. Then Jason King tuned in from Conroe Precision. Then we've got Ramesh tuned in. Ramesh tuned in from Houston. Then Isabel from Midland. David Hicks from Oklahoma. Paul McClure saying hola. I think he's on the other side of the pond. Then we've got Darius from Kuwait. Wow. LinkedIn user from Houston. Then another person, Mohammed from Kuwait. Wow. Says mom is here from across the room. Ricardo tuned in from Houston. Thank you guys all so much for being here. This is absolutely amazing. Wow, there's like more people tuning in than I could believe. Definitely got to give out to, okay, we got George. Wow, it just keeps going. George from Houston. Ayechi from Algeria. We got a lot of people tuning in from Algeria. Daryl Chicken. Who I saw on Wednesday, then I saw him on Thursday. Now he's tuning into the show on Thursday or Friday. Sorry. Appreciate all the support, Daryl. He's now working at Rival, great group of guys there. Rafael from KSA. Wow, this is like Simon tuned in from the Woodlands. Farid. When it comes to ROP, it should be Graham who talks. Thanks for the great opportunity. Graham is not a usual drilling guy. Entertain us, dear friend. Ooh, great words. All right. Lucien, I want to say this, Doha, Qatar. All right, we'll do a couple more. University of North Dakota. That's the guy who told me that? Yeah. We're talking Samuel from Aberdeen. Bobby Smith from East Texas, Curtis from the Woodlands, and the Corva group. Speaking of Corva, all right. Well, I mean, I guess we could be here all day with like the number of people that want to be able to tell them that they're too. I mean, I really do appreciate it. Thank you guys all so much. It's absolutely amazing. We'll just kind of like click them through as I'm kind of going through this right now. So we've actually got an absolutely amazing partner here with the show now. I'm really, really happy with this partnership. It's been absolutely doing some amazing things, and it helps us to be able to expand the show and do more and get more guests and do all kinds of stuff. So we are looking for you guys that are out there watching right now. Put hashtag Corva up on the screen, hashtag Corva, and get yourself a, I don't know, where did I put it? Oh, is it back behind you guys over there? Oh, it's on the shelf to your right. Second shelf. This is a new one. This is a new little drill bit that we've got. Absolutely hot off the press is the first one. I had a friend of mine specifically design this just for Gibson Reports and the show. Look at that. I don't know if it'll focus. Then if this focuses, then I become out of focus. So put in hashtag Corva right now to be able to get yourself in the drawing for the drill bit and be able to watch this amazing little insight from Corva. This is your Corva insight for this week. Here you go.
Torque and drag has always been a challenge that the industry has faced, even more now as well as becoming a lot more complex. Even though we spend a lot of time modeling and planning for worst case scenarios, we still find ourselves spending a ton of time combating these issues throughout operations. Now this is an area I think we can really improve on, and one way to do that is finding better ways to maximizing the use of all the real-time information coming from the rig side. Doing this has not always been easy though, because in the past we always had the data, but unless you had a team that was dedicated to monitoring all the information coming in and updating the models, staying on top of these trends was very manual intensive. We now have the capabilities that conducts the interpretations of all your data for you, signaling when and where you picked up, slacked off, and ringed in and out of the hole. More than ever, complex information can be simplified into quick and valuable insights, allowing all the personnel at the rig to remain in a more proactive mode versus reactive. One thing to think about is how are you maximizing the use of your data to overcome the torque and drag challenges that you may be experiencing across your operations?
All right, you guys, that was your Corva insight for this week. So now we'll throw the drawing up onto the screen. There we go. And then we will start our drawing. Here we go. 17 people entered. Woo, the record for this week. All right, let's see who the lucky winner is for the drill bit this week. And it is David Hicks. I know, David. David, congratulations, sir. I appreciate you tuning in and watching. That was your Corva insight for this week. And shoot me a DM. We'll get you a drill bit over to you right now. All right. Enough of all the intro stuff. For the whole reason that everybody's here watching is to be able to introduce our guest of the day, Graham Mensa-Wilmot. Graham, thank you so much for being here on the show today. I appreciate it, sir.
And thank you very much for having me.
Are you excited to be on the show?
Yeah.
I should say this before we get started. What are you most excited to be able to talk about?
Well, I've seen some names, and as you are going through the readout, and my mentor, RC Gupta, is here again, and that tells me I'm in trouble. But then I also saw Inzu from Kazakhstan, a very bright engineer I worked with, excellent engineer. I saw Dexter from the Philippines, and I saw my own knee, also Nia running in. And there's a young engineer I've been working with called Stephen Tete from Ghana, and I saw his name as well. So I'm happy he made it. So I'm excited about.
You're the first guest to ever take notes during the show.
Well, it's yeah, it's how I roll. You know, you got to be in the present and make sure that you know what is needed. So I'm watching everything.
All right, so tell me this: what are we going to be talking about today?
Well, I wanna get into some subjects that we talk about very frequently in our industry, but I also believe that the talk sometimes gets a little bit loose or too many assumptions around them, and we don't get to tie the loose ends to make them complete. And then you go from place to place, meeting to meeting, and it's coming up. So I think it's, sometimes I get conversations that we need to tie them in and make sure that we are all on the same page with what we talk about.
How does it make you feel when you see like either young engineers or companies that are doing exactly that? They're just going meeting to meeting to meeting to meeting and not really progressing in, what their goals or what we say that we're trying to do.
I think it's I've had mentors that always told me, you set out with an objective. And I think sometimes in defining what we want to achieve, there's no discussion or really a conversation around what it is, not just what we want to do. And so some conversations happen without definitions. And so we come into the room for a meeting. I have my view of what I think it is. You do. We talk around it. We go. And then we all do what we think we should do. And we're all right in what we want to do. But the issue is, without a definition around a subject, you can never make really measurable gains because you can't measure what you have not defined. And you cannot also improve what you have not measured. So it's a cycle that gets just rearing its head today here and tomorrow there, but it's the same thing.
So how many of these problems can we solve today? Because the last time we were on the show, we did 2 hours and 13 minutes, I think. So I know we can't cover as much as we did last time, but I know that we can dive deep on some things.
Yeah, and I think one thing I want to mention a guy that I've not seen his name there. I was looking for it, Chris Special with the HXR drilling services. As to how many of the things that I'm talking about that we can address or solve today, Chris Special, I think in the end, if I can just address some of the questions or issues that him and I have talked about, because he heard me talk one time and he gave me some really good advice. And as you know, I like people telling me what they think of what I'm doing or what I'm saying. I like that challenge. And so
give us some feedback today, please.
Yeah, Chris had a conversation around I would say the subject I'm going to talk about was indirectly driven by Chris, because he saw me talk and he said, Graham, you are trying to sell new wine in old bottles, or like they say somewhere, new old wine in new bottles, or new wine in old bottles. I don't know, but there's something there. If it's new, it's got to be in a new bottle. If you put old wine in a new bottle, people that know the old wine get confused of what they are buying. And if you put a new wine in an old bottle, whatever, it's got to work. Right?
Is that the difference between that's like, saying what we're doing and what we're actually doing?
Yeah. We and that goes back to the earlier conversation. When we say something and we've defined it, we got to do what we are saying. But you can't say something because it's the topic of the day, make people believe that that's what you want to do or are doing, but go back and drink that old wine again. That's the challenge. So we want to do that. And there's a guy else, Dexter. I hope Dexter is up at 11 p.m. in the Philippines. So I hope he stays up.
I bet there's a lot of people around the world that are up very late. I mean, we've got quite the international audience today.
Yeah.
So, all right. So let me know, how do you want to do this? Are you ready? You want to rock and roll with the presentation?
Yeah. I want to draw some distinctions between some positions that we hold on to, then establish the differences in what I believe should be done. Open myself for criticism, or people to come back and say, Graham, you said this, I don't agree. You said that, I agree. But at least the conversation should take place. We should not be tunnel visioned in what we want to do if we really want to improve. And I think that is what I would try and establish.
All right. So here's what we're gonna do, you guys. Which camera? That one. We're gonna have Graham go over. So you can go ahead and Graham's gonna go over to the a new portion of the studio, a new setup, something we've never attempted to do like this before. He's gonna give his presentation, and we'll see how this works. So and most importantly, go ahead. We want y'all's feedback. We want y'all's questions. If you have anything for Graham, let us know as he's going through this. So are you going to go help him make sure everything's set up? Okay. All right. So once he's set up, ready to go, I am as nervous as can be right now. Like, you guys have absolutely no idea. This is a project that I've been working on for, I think, like 3 years now. And we've been trying to be able to get this set up. It looks like he's in place. So, Tracy, if you would go ahead and put up the, not that one, the presentation. Yeah, that one. So here's the presentation. And then, all right, yeah, let's go ahead and put up Graham. No. Just hit camera 4. There we go. We are good. All right, Graham, you're good to go.
I'm ready. I should go.
What? There we go.
They're going to see the screen this way.
You see your
Okay.
You're good, Graham. Go.
He just needs to be able to get to it.
Okay.
It's okay. It's okay.
So all you got to do is click left and right on the arrows.
Okay. So they are seeing this, right?
Yeah, that's live right now.
All right. Okay. So thank you all very much, and really appreciate the time you joined us this morning. Thanks for those who are way back and should be asleep but are joining us today. The title, as you see, is ROP Maximization. It's a ROP Maximization versus Cycle Time Improvement. And we're going to get into optimization, holistic solutions, benchmarking, and then execution requirements. So for an overview, I'll go through what drilling efficiency is, and then talk about holistic solutions together with optimization. Then I'll get into the ROP maximization against the cycle time improvement, go through benchmarking, and then I'll do project planning, come back and do some field execution.
You want to put it up there?
Yeah.
Because that's the camera that everybody's pitching.
Okay. All right.
There we go.
Okay. All right. So then I'll get into project planning side, some field execution requirements where I introduce a new process on how to execute in the field. And then we draw together some conclusions and then see how it all ties up together. Now, I'll go through the very first part of the meeting and the presentation quickly because I want to get to the bulls and the tigers I have at the very back and not spend too much time at the beginning. But what I would want to do is to basically talk about what drilling efficiency is, and then basically go through some of the things that go into drilling efficiency. That then comes. What do we call it? Do we call it drilling optimization, also known as a performance drilling, or we should call it something different? What I'm going to be proposing and defending in the meeting. So what is drilling optimization? There are several definitions. I really do not want to try to define what it is as seen by the industry today. There's no alignment, means different things to different people, subjective opinions in conversations.
Pause real quick.
Okay, I'm paused.
Okay, go ahead. We're good.
Okay. Some of the slides don't show the whole thing. They show missing parts. I don't know if the viewership sees everything. So in that regard, and I'll get into there are several definitions, like I said earlier, and there's no consensus, all subjective. But the key KPI is on ROP maximization, and also sometimes we talk about it as to MSE minimization. But the question I would ask is this: ROP maximization and MSE minimization are the same things, but we tend to talk about them like they are two different objectives for the project, but they are the same. And so for this conversation, knowing that they are the same, we are going to dwell more on the ROP maximization aspects of drilling optimization. The focus on that is ROP, as I said, but what we should also realize, strangely, is that there's about 6 or 7 different types of ROP. It could be average, instantaneous, direct, indirect, IADC, circulation. All these measurements are available. If you give the same set of data to 5 different people and say, tell me what the ROP was, the easiest one is the IADC, which is time from here to there, divided by the footage drilled. But when you get into the analysis to understand it, there are so many different types that tend to lead to some confusions in how we do that. But regardless, as we see, then we have the mechanical efficiency parameters as well. You know, some talk about footage per day or footage in 24 hours, whatever. All those mechanical aspects are really pertaining to the same ROP conversation. Now, what are the implications? Basically, the focus is on mechanical efficiency. And then the preparations to achieve the mechanical efficiency sometimes introduces challenges from the operational side. At the same time, let me see. mechanical specific energy comes in that relationship to the ROP. So the question we need to ask ourselves, what is the intent of this effort? Is to reduce our operational cost. Therefore, does the ROP maximization lead or guarantee reduction in cost? And that is the question that, regardless of how we execute, we need to answer at the end of the day. You come to the other side of it, which is what I'm going to be talking about based on my time with Chris Special, is the holistic solutions. And here we're defining that as a process for cycle time improvement, i.e. reduction and consistency based on some execution principles and concerns, but based on the analysis of relevant data through a holistic or complete evaluation of the drilling process. Now, there are some key terms that come up as well. And so what we need to realize is the key terms being that it's a process, it's talking about efficiency and reliability, it gets into applications assessment, and then holistic evaluations or complete evaluations, and then at the end is the analysis of relevant data. So these elements come into this new definition that we are proposing to be compared to what we do today as drilling optimization. Now, if we are going to talk about cycle time improvement based on our execution of the holistic solutions approach, we cannot leave that in a vacuum. We have to define what a cycle time is. And that cycle time is the cumulative time involved in the following phases: pick up the BHA, drill out, drill ahead, trip out, run the casing, and anything you may do, any trips that you may have to do based on what happens in the drilling. So we add all that time, and that is our cycle time as we are defining now for the holistic approach to improvement. Now, this goes way beyond what we've normally seen for the ROP maximization, which barely looks at my on-bottom or drill ahead activity. So the question again, as I asked earlier, does this approach guarantee reduction in operational costs? And if that is the case, let's now look at it and show that we get that intent from that definition. Now, so we talked about holistic solutions, we talked about cycle time improvement, and we also talked about the achievement of specific operational requirements when we defined drilling efficiency. So those requirements have to now be defined. So in talking to you or talking to him, we all know what we are talking about. The diagram you see is a diagram of the cycle time factors that are operational considerations that must be achieved to reduce my cycle time. Now, as you see, these elements are all known in the industry. We deal with them every day, but it's how we treat them and how we assess them. So basically, what we are saying today is that these elements that we've always known are all related, and we cannot discuss them in isolation. I can't come to you and say, well, I'm doing well because I'm drilling fast. I'm doing well because I'm drilling long. I'm doing well because my torque is low or my vibrations are low. No, those conversations are in isolation that we can't tolerate if we want to move ahead. We need to sit down and say, these are the elements. How do they affect my performance? Which ones are more critical? And how do I design my system and execute to achieve them? The process of saying, let me go improve ROP. If I get ROP improvement, then I'm going to go fix a new limiter or something to drill longer. Then I'm going to, that is way too old as a process. And it takes too much time. If we sit down and assess that system, we move faster because, as you can see, they're all related. But the key is that the relationships are not inverse. Because today we say, if I drill long, then I'm going to drill slow. That is not true. You can drill long and fast. You can drill long and steer. You can drill long and also manage or control your vibrations at the same time. So, but the key is this. If you look very closely at the diagram, even though I'm talking about operational aspects, ROP, which is the mechanical input, is part of it. What does that mean? ROP is not the condition that must be maximized or achieved as per my earlier conversation on the optimization aspects of improvement. and that ROP is one of several. That's the key. ROP is one of several when we want to improve. Let me give you a quick example of a well drilled where the time involved by the two processes are measured. So you see the ROP maximization and the time involved in it on the ROP side and the cycle time side. If you look at the percentage of those two measurements based on the contributions to the percentage of the total section time, the cycle time approach is much bigger. What does that mean? That if we bring up this conversation and make our industry and our stakeholders realize that this approach of cycle time reduction or improvement has a bigger effect on what we are doing in drilling. Because most times you're talking to somebody and he says, well, I don't care about ROP because it's only 10, 12, 8% of my drilling time. Because that person is just looking at my drill ahead. Because when you can run pipe after I've drilled a well, there are things that I could have done in my evolution and in my complete analysis of the system to make you get a better hole to run pipe. So that is part of what we, the holistic solution pursuers, are describing today. Measure us by the cycle time as I've defined it and not based on my drill ahead time as is currently done in what we do. Now, what happened? I think I'm trying to move forward. There's no moving ahead. The next slide.
Which slide do you need to be on?
The next one.
10?
Yeah.
There.
Okay, all right. Now, here I'm showing an example of a project where the two systems are used. So in phase one of the project, they are drilling a well. You can see the BHA breakdown, the bit type BHA running 2 BHAs for the section. And then the next time, as they go through the second phase, also the same thing, then there's a need to improve. And then the conversation comes up, do we do the ROP maximization approach or will we do the cycle time? Say, well, as a new process of what do you call of learning, you know, let's all learn to grow. So you see the yellow line, which is the third one, again in the project, we decide to get a BHA that is packed and put in a bit with that and decide to go back and push it to drill faster. That was what was done, which is again an optimization approach based on the ROP maximization as I've talked about earlier. When we did that, we drilled very fast, finished the section in a single run, go to TD, very good door, but look at our deviation, 9 degrees. If you go back to my definition of drilling efficiency, I mentioned the drilling of a usable well bore as per plan. Building to 9 degrees made that well bore, regardless of the ROP and how it was, useless. And we spent time for the correction that time today, by my definition of the cycle time, would have been captured. So the ROP measurement was great, but that time that we spent for the correction made that gain totally useless. So operationally, mechanically, yes, but operationally, no. So on the next project, as you can see in the green, we didn't do that, went to the holistic approach of getting that whole thing to work, and then ROP was down, went from 64 to 53, got to TD, but if you look at deviation, it was just 2 degrees. So we drilled a vertical hole, and we didn't have to spend all the back time to do the things that the other well made us do. And that was a big gain to the improvement that we're seeking. Now here, I'm just summarizing what it used to be. So remember the earlier diagram I showed of the elements that I said are all interrelated and linked, and that ROP was one of them? If you took that diagram of all the elements and you said, this project, what are my most critical concerns that need to be achieved, where what I call showstoppers, something that if not achieved can cause me to incur big costs or really exacerbate my challenges and make me very inefficient, you rank those and then you set out to achieve them. So if you look at this slide, we have a borehole verticality at 40%, torque behavior with regards to vibration at 25, footage at 20%, and you rank all of them and you design your system and execute to do that. And then the conditions that we had were, one, the need to have a specialized build to help us drill vertical in an area that was very difficult to hold verticality. Two, the BHA design. Instead of the pad to push on more weight to drill faster, we went to a pendulum which we knew had to be run with less weight to make it stay on vertical, to help us drill to vertical, because the pendulum allows you to make the corrections through your rotating events as against pushing hard on the pad. And that change together, and also realizing that the bend size we use has a big effect on the durability and our vibrations as well. So if we want to do that and go pendulum, then we also have to manage our bend size to make sure we can drill. So, and the risk and the RPM limitations based on the bend also came in the analysis. And in the end, we also changed the bit. So we are changing the model, changing the BHA to pendulum. We are doing everything around what to make us improve, not thinking of what to change to go drill faster. That was never the objective. It was meeting those elements I've listed based on the percentage contribution to success and cost reduction. That was our driver with the project. Now, here I'm just showing the cycle time. So the box in red was the best performer on all the offsets. And what happened was when we went to the holistic solutions, bringing the cycle time down. So you see, I'm not plotting ROP max. I'm plotting cycle time by the definition I gave earlier. And the issue, or what is clear in our minds, if I maximize ROP, there's no guarantee for cycle time reduction or cost reduction. But if I reduce my cycle time, my cost always goes down. Superintendent and operational teams are more interested in the well cost, which is driven by the cycle time and the days on the well. That's what is important, and not how fast I've drilled in a section. I'm not in any way saying or claiming ROP is not important. Far from that. If a project requires me to increase ROP, knowing what effect that has on all the other things that need to be done or achieved, then we go for it. But I can't start a project with the intent to maximize the ROP without knowing how it relates to the other things that you saw in the earlier diagram. That should not be how we drive our performance and cost reduction. Now, let's look at something here. I'm here listing drilling parameters that we see, inputs and outputs. I'm doing this because I'm going to get into the next phase of our conversation, which is benchmarking. Having talked about already, I finished the side on the optimization and the cycle time, which one is more important and brings our costs down. Now moving into the benchmarking side. But I need to separate my parameters into two, inputs and outputs. Because when we talk about benchmarking, in a way, we're talking about efficiency in our minds and how it can help us do better, especially when we do our lookbacks going through the benchmarking process. Having done that, we have inputs and outputs. So we are going to compare how outputs relate to the inputs. So we have weight on bed, RPM as inputs, and the other ones you see in green as my outputs. And we know something else. Vibrations is an interpreted output. So we measure certain things around the parameters and we decide that, oh, we are vibrating and this is the mode of vibration back and forth. But because it's an interpretation, you will see that the same project, when we come to the vibration conversation, the modes could be defined or identified differently based on the tools you are using and which service company you're working with in their processes. So that is not an easier thing to do that quickly. Now, benchmarking. So what does it really require? What does it entail? It's the process to compare output parameters at normalized input parameters. So output parameters at normalized input parameters. We can benchmark because this one drilled longer or faster, just like that. We got to look at how and why that came about. Because sometimes you see that what you may see or think not to have been good in your process actually was the best run if you go back and look at how that run came about. So in this diagram, I have like say 3. This is where I get really psychedelic with all these things that David is giving me. So I have 3 runs, as you can see. Okay. Now, if I compare these 3 runs, and let's say, for example, if I have an output here, and I have an input here. Okay, and the input, as you saw, could be weight on bed, flow rate, whatever you want to call it. And the output could be footage, vibration, whatever it is. Now, if this is A, and that is B, and that is C, if the runs were such that A did that much, because this was my input, and C had an output that was here, which was higher than what the A did. But realistically, C had more of whatever was needed to get that result. So if I come out and look at the data, and I don't get into this analysis and I claim that, oh, C is better, it is not. Because it is using more input to get the output. Now, let's do something. What happens if I then said, let me compare A, B, and C normalized conditions based on what C got? So I come back and now extend to the A and the B for C. So if I give C $1,000 to go shopping, I better give B and C $1,000 to go shopping. If I give you $1,000 and I give him $50 and he brought me 1 shoe and C brought me 10 shoes, and I say C is the better shopper because he knows how to bargain with it when he goes to the mall or goes to the store. No, I give him more money. Now, I'm gonna also say something here. There are people that will tell you when they begin to use certain equations or processes, they'll tell you that, oh, you know something? When you want to use, like, for example, MSC to do your efficiency measurement, the first part of the MSC, which has the weight over the area of the borehole, neglect that because it's so small to the whole MSC output that you don't have to do that. Wait a minute. You're telling me to drive to Dallas. You give me a very big car that needs 80 gallons to get to Dallas, but you don't want to know how much gas I put in the car or how much money I'm giving you, but you're going to tell when I get to Dallas. That's not how it works. You have to look at every parameter that is in the drilling process. That is why I came up and I started out with input and parameters. You cannot neglect weight on bit. When weight on bit is what drives torque and ROP. And tell me you're going to measure ROP and see how well it is, how big it is, without the need to evaluate what drove the ROP. That process cannot be how we manage, benchmark, and evaluate. We got to look at them at the same input conditions. Okay. Yes, sir. Excuse me. I can't go to the next slide. How do I?
Okay. You have to click on this one.
This one?
Don't remove. Let me see. That is the next slide.
That's the next slide? Which one?
All right, go ahead, Grant, but LinkedIn's flipping it on its own.
Oh, okay. So how do I get to my next slide?
I'll put it up on the screen.
Okay, thank you.
There it is.
Okay. All right. So now that we've shown how that benchmarking has to be done by our analysis of output parameters at normalized input conditions. Let's now look at certain conversations that I think are very critical before we move to the field requirements in performance. So, in the planning stage, as per the new process I'm talking about, which is the holistic, looking at the cycle time and the factors that I listed earlier, we need to have a very good conversation on formation drillability, and then hole size, the physical versus functional aspects of what we do, have an understanding of what the similarities or differences or relationships are between failure, durability, and longevity. Then we come to the rock mechanics itself. There's so many of these elements that need to be understood, but for time, I'm going to pick on a few of them just to help establish what I'm talking about on the holistic side of the conversation. Okay. Now, let's look at the formation drillability aspects of it. We've been made to believe that the harder the rock, the slower you will drill, the more BHAs you will run, the lower your ROP and all that stuff there. And that if the rock is softer in terms of the strength, whether it's UCS or CCS, then you should be drilling faster or longer or whatever it is. So you sit back and you say, there's the field observations that you see. When you compare to the claims and the theories around this conversation, does it hold? My experience says no. And that when I look at the rock effect, I come to a certain position called the formation drillability and its contributions to drilling difficulty. So drilling difficulty exposes me to how likely I am to succeed in my operation. And in that context, the rock you see, if I have two sections of, let's say, the same lithology, and one of them is got hard 0 to 40,000 psi, 0 to 40, and one of them looks like this. Okay, on average, we know it is lower. On average, it's lower than this one. This one here, as I'm calling A, is much more difficult to drill, more likely to cause two failures, challenging with my directional work and everything else compared to this one, B. But that, if this realization then exposes us to a different conversation, that hardness is not as critical as the heterogeneity and how that contributes to the dynamic events around the drilling. So now let's look at a second subject. If I now have two sections to drill, okay, let me go back. Let me use. Let me clean this one again. Yeah. Okay. So as Tracy is helping me clean, if you could clean just the line for me, then I'll be able to. Okay. All right. Okay. Yeah. So if I'm going to do something now. If I have two intervals to drill again, and I have the same average hardness for the interval, same length H, and same length H, and I have two lithologies, limestone and sandstone. So I have limestone here and sandstone there, same hardness, and now I have sandstone and limestone, same hardness, but the sequencing of the lithologies is different, but it's the same hardness. So let's say this one's hardness for the section, let's say it's 30,000 psi, and this one here is also 30,000 for the two of them. But our current position around drilling optimization today and the claims we make about the difficulty of the drilling based on our hardness and how it pertains to what we say that when we are in 100% drilling efficiency, what that rock strength should be when compared to our MSC, for example. Okay, these two should drill the same. The MSC should be the same if my bit and BHA is the same for the two of them. But you will see in the field that that conversation is not the case. When I have a section where my formation, the drillability of two different lithologies, but their sequencing is different, I can do the same comparison for shale limestone, limestone shale. I can combine them in any way. I just told you two for simplicity. The section where I drill the limestone first and the sandstone second, when the hardness is similar to the second option, drills better when I have sandstone on top and limestone below. Not even close. Now, if the hardness is the same, and because of the sequencing in the lithology, my ROP for the section will be different. Then my MSC will also be different. And if MSC is supposed to be equal at 100% efficiency to my rock strength, and the rock strength is the same, then the MSC should have been the same. But it is not. So how then do we relate the claim of 100% efficiency in value of my rock strength to the MSC? I'll leave that for another day's conversation because David is going to tell me I'm running out of time here. Now, Where's my next slide? David, next slide. Okay. And digitalize this cleaning. I love it, but yeah. So on the next conversation, after having talked about the importance of formation drillability in the holistic approach, because in the holistic approach, I'm not looking at the hardness, I'm looking at the drillability and the difficulty of the section to make sure my system design, BHA, everything else comes into play for me to be more successful. Now I'm going to talk about something else. In the past, especially when I used to look like Michael Jackson with an afro, we were told and learned that if I have two, say, bits, and they have two different cutter sizes, the bigger one, the bigger cutter, compared to the smaller one, my ROP is better for the bigger cutter. That's true. We are designing these bits now, and also, the fact that what we do to the bodies of the bits on and on, that claim is not true. So if I have two cutters of different sizes, there are conversations. If I do laboratory testing to verify the impact resistance of these two cutters in the lab, the bigger cutter needs more joules or more energy to fail than the smaller one. But if I took two bits to the field and I had a 6-bladed bit, for example, with 16mm cutters, and then 6-bladed bit with 19mm cutters, in the field, even though in the lab, I've shown that the impact resistance of the 19 is better than the 16. In the field, I see that the 16mm bit door under this condition is better than the 19 mil. Now, so you have two data sets in two observations in conflict. The lab says the 19 is better, but in the field, the 16 is better. So the question then becomes, why? Because in the field, you are not testing the cutter size. You are testing the bit, and the bit is driven by the cutter count. The count conversation is lost, and we are making decisions on what a 19mm cutter can do in the field, forgetting that the count is different. This bit may have 60 cutters in it, and that bit may have 40 cutters in it. In the field, you are testing this number and that number, not the 19 mil and the 60 mil. So sometimes the data in the holistic approach, we do it differently. I will not come and argue that a 19 mil is not like that. No, because I know that if I got what I call an equivalent bit in 19 mil to the 60 mil, I will do different things. And that's why the holistic approach and the system verification comes in. Second, I've thought about how now I cannot claim that 19 mil is faster than 60 mil. And the impact resistance comes into play and is an issue. Now, when I design bits or have bits in the field, our parameter ranges on and on. Now, some people also will argue that, 19mm cutter was going to vibrate because 19mm. No, cutters don't vibrate because of the size of the cutter. The bits don't vibrate. It's not the size of the cutter that is making you vibrate. It is the design of the bit with that cutter that is making you vibrate. So again, the observation is there. If I run this bit and then I run that bit in the field, my torque is higher here than here. Now, we tend to associate higher torque with vibrations. Vibrations is more dependent on the behavior of the torque, not on the magnitude. So, but then I'm not going to claim that, if it's higher in magnitude, the susceptibility to the vibration is not there. It is there, but it is within my means to control. If I understand the design, and I'm going to touch on that very briefly because David is already waving, but look at this slide. Okay, let's go back to this slide. I'm showing you 3 comparisons of bits. This here, the one you see bottom left, it's a 7-bladed bit, 60mm cutters, against a 9-bladed bit with 60mm cutters. The 9-bladed bit with 60mm cutters is faster, is more durable, and drilled longer than the one with the 7. So all the things that at least we will say, we can accept that physically the 7 will be faster, but the 9 will be slower. That is not true. Now you go to the one on the top. I have an 8-bladed bit with a 6-bladed bit. And again, the same conversation. The one on the left, which is 8, faster, more stable, more durable. Then you come to the one on the bottom, and that's where it really gets exciting. I have two bits. One is steel, one is matrix. And we know that the steel body bit has got all the benefits around hydraulics, blade height, blade. Then you look at the bit on the right. It's matrix with 6 blades, 60 millimeter cutters. And the one on the right is faster than the one on the left. So not only is a 6 blade to 6 blade conversation showing that a 6 blade 16 millimeter cutter bit can be faster. Now, as to the conversation about which one is more durable, which one is going to be more stable, I'll leave that out. But the one on the left is faster than the one on the left. And this is 6 to 6, 16 mil to 19 mil. So, and it's also body type comparison. I have a steel body bit with all the improvements and elevation in phase volume and all that stuff, and still our claims that we make does not hold. So we need to step back and sometimes now begin to evaluate our perceptions more. We need to close the links and not just take the data as they come in, but what is driving the data? Why is this happening? Why am I not seeing this my expectation? Those questions are left. We don't talk about them. We just see the numbers. We make our benchmarking. Like I said, you got to go back and normalize outputs to the inputs, and that's what is going to be very helpful as well. Okay, so let me now, what's the next slide? Okay, go back. Okay, now I'm now going to get into a subject here. 3 bits, and again, I'm referencing the paper from which it comes from. 3 bits tested in the lab. 1 bit is got 8 blades with 30 millimeter cutters and lower back rake. The second one has got 9 blades with 13 and 16 millimeter cutters, 13 and 9 millimeter cutters, 9 blades. And the third one has got 8 blades with 13, 9, and 11 cutters in it. Okay. Now, the bit, let me use it right. So the bit with the bigger cutters all average throughout, which is the X bit, is the slowest. So a bit with bigger cutters throughout, with lower back rake in the lab, is slower than the 2 that are smaller cutters and more, and the one that's going to be more blades. So conversations around they don't hold anymore because we are doing so many exotic things to these products and stuff that those claims don't hold. So, but why is this diagram important? As you look at the 3 bits and the ROP response to weight, by the way, RPM is constant in these evaluations. So is the nozzle count, the TFA, and the flow rate. All those things are kept constant. The only difference is the weight and measuring the ROP. Okay, now, if you look at those diagrams very carefully, those lines very carefully, you see lines that look like this. Okay. That line that looks like that defines the 2 rock failure mechanisms of the bit. And it's very critical for our ensuing conversations for us to know what I'm going to be catching on here. So if I have RPM is constant, so is flow rate, TFA, everything is constant. And I have my weight on bit here. And I'm measuring ROP here. As I do a drill-off test or as I apply parameters, I see an ROP increase anytime the weight on bit goes up. It gets to a point where the same finite increase in weight on bit gives me a non-proportional or an exaggerated increase in ROP. That depth or that value of weight at which I see the deviation from my trend, because normally in this trend starting from here, my trend should have gone like that, but it doesn't do that. It's a no-no. It will change there. So I will characterize this condition as scraping of the formation and then shearing of the formation. And these 2 conditions are so critical and are needed for us to understand as we move forward to understand our performances, especially in the field. So anytime you see this now, I'm going to also show a different diagram where I'm going to differentiate that. So what am I seeing here? What I'm seeing is that this bit, if this was bit X, and this is bit Y, bit X is taking much more weight, WX, to transition from scraping to shearing. So the condition is, what is the difference between the two, and why is that important? And why do I care about this transition? I care because the heat the cutters see on the bit changes based on that transition. If I stay in this zone longer, it doesn't matter how many cutters, how many blades I have on the bit, I'll build up more heat and I'll wear it faster. If I transition to my shear quicker, like what this one is doing, let's say I'm running these two bits and I'm running this weight here. I'm running this weight here. And this one is giving me this ROP, and this one is giving me this ROP here. The significance of the mechanism of failure is much more important than the ROP, because in addition to this ROP being higher, it is building up much less heat in the bit, and therefore less likely to start to wear compared to this one, which is drilling slower and wearing, and also going to be wearing the heat. What does this mean? Sometimes we, in optimization, will pull a bit, and the bit is worn, maybe 2, 3, 2, 4, whatever it is. And we say, oh, let's go get a more durable bit. What does that mean? A more durable means let's go find a bit with smaller cutters and more blades, and we can increase the number of cutters to do that. What have we just done? We have just forced the bit that was scraping to now guarantee is going to be scraping more and longer. So it's like going to the kitchen and you find out that, oh, the knife you're using to cut your tomatoes is blunt. You cannot cut. And you say, wait a minute. Now let me put more force to cut a tomato. But in doing that, let me get a blunter knife. That's what we're doing. And in the holistic approach to the solutions, we don't do it like that. So with this conversation, let me now transition to a more critical implication. David, give me next slide. Now, this slide here, okay, all right. Okay. Okay, so I have yeah. Okay. Oh, I like this color. This glowing is nice. Okay, so now let's look at these two diagrams as you saw earlier. Okay, and I thought about the heat. So what does that heat diagram mean? Remember that one condition I kept constant was the RPM. So if RPM is constant, then I can equate, if RPM is constant and my flow rate and everything else is constant, then I can equate my ROP to my depth of cut. If RPM and flow rate and HSI are all constant. Otherwise, the two of them are so different in how we should understand and interpret them. But because I kept that constant, I'm going to make that conversion in the discussion. So the ROP I was getting, based on these conditions here, I'm now going to bring them into my heat diagram. And we know that heat we build in a bit is a function of the friction we create whilst drilling, which is also dependent on my depth of cut, which now I'm going to be equating friction from the rock, the abrasiveness of the rock, then my depth of cut, which I'm not going to be equating to my ROP because my RPM is the same, and then the time I stay in the hole. That's what I'm building up on the heat. And I can add other things like RPM and all that stuff, but that's those drivers contribute, but they don't dictate as these three elements I've talked about here. Now, actually, there's a paper written by Alan Sino. Alan Sino wrote a Bible to me, SPE 39306. This conversation that I'm having, especially here, Alan Sino described all this years back, about 25 years ago. And the concepts have not changed. We have just neglected his teachings. So let's go back to my heat diagram. Now, I'm going to plot, look at this line here. Okay, so anytime David, can you go on the screen? Make it bigger for me? Yeah. Okay, so anytime we are on this part of the diagram, anytime we are here, we are going to wear the bit. Anytime we are here, we don't wear the bit. Okay, we don't build heat. This is a heat diagram. So we want, and we have abrasiveness on this side and my depth of cut on this side. Okay, so we want to stay here. We want to stay in this. We want to stay here. Now, this, what I'm saying, has been tested and proven in the lab over and over and in the field. It's not anything new. It's just the application of these principles through the physics to the field. But it's been proven. I want to stay here. I want to stay here. And I don't want to be here. What does that mean? If I want to minimize my wear, let's say I have a bit here that is wearing because of the abrasiveness of the rock and my depth of cut, which is low, I'm in this region. I'm going to wear. So it doesn't matter. So if you want to improve your ROP, sustain it longer and drill longer, you don't put a very heavy, a very heavy set with tons and tons like a tank, because then you are going to reduce your depth of cut, and if the rock gives you any abrasiveness, you are going to entertain the wear. And as we know, wear begets wear. As you start to wear, the minimal wear grows into bigger wear and very fast. So if I am here and I want to improve durability and drill longer, faster, I cannot change the rock, which means I cannot come down in this conversation. I cannot come down here because the rock is the rock. The Travis Peak, the Plover, the Wamampampa does not change. But if I'm here and I want to drill longer and faster, I can go horizontal and come here. Because if I come here, I'm falling below my heat diagram. And how do I do that? This one here, my depth of cut. Now, does the depth of cut alone do that? Come back to this diagram. No. Because when I'm scraping the rock and I increase my weight from here to there, I'm still seeing an improvement in my depth of cut or ROP. I've seen it. But have I changed the rock failure mechanism of the scrape and the shear? No, because the gain in the depth of cut resulting from my weight on bed increase did not change my slope. If I don't come here, it doesn't matter how much weight I'm putting, I'm still going to wear. I need to come here and minimize or reduce the heat I'm building up in the cutter and in the bed. So, Tracy, can you help me? And David, give me next slide, please. Now, this conversation that I've built up was leading to this point. We know that when you increase weight, and there's no, again, when Alan Siner talked about this conversation, he talked about the need to be dynamically, to fill our tools or bits in a static way, which means devoid of the mechanical or vibrational input. So he said that if I'm not vibrating, which we have to work on with our BHA design, our parameters, and our bit design selection, and I'm just looking at the wear side of the conversation, then this conversation comes in. So if I increase weight and I'm drilling faster, because there was a time when we were so scared of increasing weight, thinking that, oh, if we increase weight, we're going to break something, the big impact. But then we've seen that increasing the weight does not really lead to that. But then there's still some skepticism around doing that. So, but the issue, as I've just pointed out, is not the weight increase. It's the depth of cut change and the transition from the scraping to the shearing. That is what is driving the mechanism. So look at this slide. David, make it bigger. Okay, I want to explain. Okay, so if I have the same formation hardness throughout, and I drill the first well 4,000 feet in the blue, and is my benchmark, great run, and I get 1-2 dull condition. Okay, now if I go to my next well and I'm told to drill 8,000 feet, oh, I need to run two. No. If we understand that the ROP, which at the same RPM, is equal to my depth of cut, and the depth of cut's contribution to my shear scrape, and the shear scrape's effect on my heat, and the heat effect on the wear, that's the chain we need to build. So if we want to break the wear conversation, we need to break the chain. Why do you build a chain? Make sure that that you establish a good condition devoid of the dynamic input to the failure, and make sure that your depth of cut gives you a shearing mode, which means you have to drill faster. If you do that, you can drill longer and come out in a better or the same door condition as the one you just had. Okay, so, but if you are thinking that, oh, because it is going to be a longer well, what I call my rotating distance is going to be more, I'm going to be spending more time in the hole, so I'm going to be wearing, and you're explaining your wear due to the fact that you drew the longer hole and you're more time in the hole. No. When you say that increasing weight will make you drill faster, that is true, because regardless of the mode of failure, if I'm here, there, if I increase the weight from here to there, my ROP goes up, but my wear effect does not change because I'm still scraping. I need to get here. Now, let me pause for a moment. We are talking about depth of cut, and I'm using the weight conversation, but you can tell me, Graham, you're on the wrong path, and you are right, because there's another way of doing that. If I also had a bit in a BHA where that bit didn't need that much weight to shear, let me draw one more line so you see what I'm getting at. If I had a bit that did this, where at that same weight that I went from, so I went from 10,000 to say 30, and I'm still scraping. But if I had a different system where at the 10 to 30 is now in shear, I solve the problem. So sometimes you want to increase that weight to 60 to transition, but you can do it the other way around. Find something different, analyze it, divide all the mechanical input, and then you run and you get into shearing. That's it. So this conversation is so critical. We don't wear because we drill long. We are wearing because we are not changing the failure mechanism that the bit is giving to the rock. We are staying in shear, in scraping, and that's what is happening. It's not how long we've drilled. There are offsets where you run something, you drill, longer, and it come out green and say, oh, maybe no. I've had people tell me, well, I think the rock was different, it was softer. No, it was not, because I applied a holistic interpretation of the application, and that's what led to that. It's not because the rock is changed. I remember one time, anyway, I don't want to talk about digressions, but David, give me next slide. Okay, so when we talk of vibrations, we have to look at it because it's critical to the conversation I just had. So the question is, you are talking about a medium devoid of vibrations or the dynamic input being minimal before sinus teachings can come into play. That is true. So how do we do that? We need to make sure that we are analyzing what could possibly be causing our vibrations holistically. On this slide, I have all the conditions, factors that could create vibrations. The BHA, the drive system, whether it's a push or point, because those two have different dominant vibration modes. The conversation around the fact that because the pipe or the string is in constant rotation and therefore not sliding, therefore not vibrating, is not true. The two contribute to the vibrations. And it's been proven the formations characteristics, as I showed earlier, the hole size, the parameters we run, the bit we've chosen can contribute to that. If there's a reamer in the hole, all these elements contribute to that and should be analyzed as per conditional application. Now, give me next slide. So here, if you look at the list I've given, I'm going to pick on what we all subscribe to being the culprit. There's a problem, we point to him. Hey, that went bad. Oh, Graham is at fault. That went bad. David, today I've not picked on you. I'm coming. Don't go too far. So basically, you have the vibrations. So the bit, when it's picked of the list of factors that could contribute at the system level, then I come to the bit's contribution to the vibration and the elements or what around the bit can drive that. So I look at vibrations from two aspects in control. How can prevent and or mitigate. So what aspects about the bit, what do I care about more? I don't need to mitigate something that is not there. So in my pursuit, I want to say, okay, I want to prevent. And so what around the bit helps me prevent vibrations. Profile of the bit is critical in the prevention side. The cutting structure of the bit, this is not the cutter size. It's the cutting structure. It's how the bits are designed and laid out to achieve specific objectives. That is critical. Then the last one is the force balance on the, how you balance the bit. Very, very critical. There's so much evidence on this to the dynamic behavior of the bits, but today we don't even do it. We don't, I mean, it's like, oh, just, no, it's like it's gone. It's a lost art. I remember when Martin Fear was in BP in Colombia, and you had to, you know, balance and explain this, and he was measuring all that stuff. The paper's written, is all there. Okay, so let me step back. Now, if you have the preventive side, then you have the mitigative side. And let's realize that mitigation comes at some expense. If you are going to mitigate, like I'm sitting down and I know that, man, I want to lose weight, and I know the implications of being fat. Okay, I'm talking about myself now because I've been told by the doctor to lose weight. So if I'm not doing what is required, then I want to do the preventive side, which is what? Taking this medicine. You know, we all know the implications of medicines, but the best medicine is for me to lose weight. So anytime you engage in mitigative aspects of control, it comes as an expense. If you want to put some features on a bit to try and minimize or do something, it's not free. But if you can solve the problem for the preventive side, you're not losing anything. So I'm a strong believer to understand the profile, to understand the cutting structure, and to understand the balancing. If I do this right, and I use 20% of what I have to do next for mitigation, and not the other way around, where I'm doing something and I'm going to put a lot of mitigative aspects because I'm trying to control my vibration. But what I just want to show is the level of things that go into how a bit can contribute to the vibrations we see. Next slide, David. Okay, now the diagram you see on the left is a classic one which has been published in several papers by different authors. So you have this and you have that, and then we are told that this is where the weight on bit is low, and this is where it's a constant slope, and then you get to a flanner point and it comes down. Now I want to, and this is what we are. So basically, if I want more ROP and I'm here, I increase the weight. And if I want here and I have to redesign something, come back, work on that one and get me to be able to increase the weight from W1 to W2 to drill faster. The holistic approach does not subscribe to this position. First, this one here, if I go to the field, what I see in the field on the relationship between weight and the ROP is very different from what it is saying. And by the way, clear distinction. When I draw this and I have two slopes, that is not the same as this. This region of a constant slope, K1, is what I'm talking about and saying that now in the holistic interpretation to the development, it's got two slopes. So this region has got one slope. This has got two. So this has got K1 and K2. So please, this one here is still here. I don't care for that one. When I'm tagging bottom, I'm spotting the, I'm not, that is not what I'm talking about. I'm talking about this here, which is 2 compared to 1. And this conversation has lots and lots of implications. The biggest one today is what this discussion makes us do in the field on the assumption here. Why is that? Why is that needed? That single slope is needed because of the claim that if we're 100% efficient, MSC is constant, and then ROP is the best you can be in the sweet spot. Okay, that requires this slope to be constant. That slope in this region, you have 2 like that. You have the script and the shear, and there's 2 different slopes. And I want to be here. That is not the same as what we are talking about here. Very different conversation. So, David, can you bring my slides up and then blow it up? Okay. So, in the field, this is what we see on the right. Okay. Now, in that, so you see different ROP behaviors to the weight. It's not a straight line and the extension of that. I'm seeing all this here. And every time you get data and you don't do the averaging, which we do, or the average weight on bit, but you go into understanding what is going on, because this is going to tell you exactly how your system is behaving, how your BHA is behaving, what is happening. That is what you see in the field in real life. Now, if you relate that back to the bottom one, where I'm talking about the script shear, that's a conversation. But in the field, you are seeing the right one, which I'm calling the holistic solution slide to the ROP to the weight response. So David, give me the next slide. When we base our conversations on that earlier slide, which I'm talking about, it makes us believe that ROP goes down, I need to put more weight. If the ROP is, if I see torque fluctuation, it sticks there. That conversation is driven most of what we do today. But let's draw back, look at the data and not average them. Look at the zones of the drilling, what is happening, and then you begin to see trends that are very different in that data. Because the passion or the path to improvement is in knowing, it's just not being aware of the problem, but knowing what is causing it and the why and the hows that happens. David, next slide. So if we go back, I don't know what it, okay, if we go back to what I said earlier, that you have to recognize what is happening. And what I want to say is this: when you recognize or know that you are sick, it does not mean that you know what sickness you have. What does that mean? I can tell when I'm vibrating. That doesn't mean I know what I have. Or I can tell when my ROP is not responding the way it should be, but I cannot tell what is causing it to be until I go back and look at a new process that I'm going to be describing, which I call the AIVReC. AIVReC. AIVReC is AIVREC. AIVReC. And what does that mean? It's a 5-step process to the identification and remediation of dysfunctions in real time. A stands for awareness, then I for identification, V for validation, RE for the remediation, and then C for the confirmation. I do not want to jump from an awareness to a remediation. I don't want to do that. I don't want to see just RPM fluctuate or torque fluctuate or ROP go down and say, I know what it is, boom, let's do that. No. I want to be able to understand what it is, what is causing it, validate that, and then before I do that. And there's a way where all the dysfunctions you see, we can define them to go through this process. Now, somebody is going to say, Graham, this is a long process. It's not. You do it 1 or 2 times, it becomes innate. It becomes like that. And you can see, especially if I'm in the same area doing it, it becomes automatic and part of me. But it doesn't mean that you just have to do the work and get to the point where you can recognize it quickly. So David, let's go to the next slide for me, please. So let's not become aware and then jump to remediation. You become aware, you identify, you validate. So let me draw one quick one. Okay. All right. Let me use one little space here. Okay. So if I look at data and I see my ROP. Oh, David, all the time I'm losing, I'm going to be charging to you. Okay. So if I see my ROP to the weight on bit and I see this, it's not the same as this. This is different, but I can see this, which tells me that as I increase the weight, ROP is going up. I can't validate that I'm in the script shear mode because I don't see the change in the slope K1 to K2. But what I can confirm is this, that is coming down. Now, that is an awareness of a trend. I need to identify all the things that could have caused it. And then I need to also have a way of testing to eliminate by the Kepler trigger process or something, say, if A, then B, if B, then C. I need to do that before I can tell that this trend I'm seeing is caused by this because, and this is what I do to fix it, and this is what I did, and I fixed it, and therefore I knew what it was. Without that process of reacting, somebody will say, oh, the ROP is going to increase more weight. If you increase the weight, it's going to be worse. Then they go, oh, so this is the challenge that we have that I think that we can all work together, engage, discuss, and make ourselves better. So let's go to the next slide, David. This is the recent run where, no, go back, the one before this one, okay. And give me full blast. Okay, so here I'm showing some parameters. The left one is the RPM, RPM, total RPM. I have the next one, which is the weight. The next one is Yeah. Okay. All right. So I have those parameter trends. Now, it became very obvious right from the very beginning of the run that our ROP was lower than expectation. We've drilled several wells in this area recently, and we started out, we're in the 120 foot an hour, the same weight. You know, it's not like an unknown. So we knew there was something wrong. Now, we start trying to go through the process of identifying it back and forth, and nothing is working, or we knew there was something wrong. So you go into the data and you begin to look at the trends in the data. If I average the data, I will never see what is happening. But if I go back and apply the trends I showed you in the weight response back and forth, the issue becomes very clear, because every dysfunction has a definition, and it's not just a definition. We also have parameter trends that help you identify it. It's not what some computer mode is saying. You know, when you work with the guys in the field, and I'm looking at the real-time data and stuff, you can see it. So, David, blast me up with a full slide on that one, and let me see. Yeah, give me full blast. So, you're looking at this data. You see certain trends, and the trend is matching. The trend is matching the one I talked about earlier. Is matching this one. Okay, so basically, when we back off the weight, so when you do that, there's so in the beginning, the question was, is it this? Is it this? Where I'm increasing the weight that I'm balling, but if I was balling, I will see. If I was balling, it could be this or it could be that. But this one here, sometimes these two in their readout in the data become very, very close in the interpretation. That is why I made a comment earlier that when you validate, there are ways to cross-check. If you believe that, so one, this could be caused from weight hanging up. It could be caused from the bit. If in a way, based on what we're doing, it could be also be caused by balling. It could be caused by weight hanging up. It could be caused by the bit wearing. So many things could cause that. But I'm not going to jump into the conclusion until I check it. So the very first thing is, if you are balling, the question is, did we know we're in a zone that could cause us to ball? Because we've drilled about 8 wells, and we've never seen this ROP be that bad at that weight and everything else. Okay. Now, also, it could be caused by formation change. That, hey, we're in a different formation that we didn't know, and all of a sudden it's causing that. So that conversation comes up. So, in a way, knowing that trend, you go through your definitions that if I'm wearing this, if I'm balling this, if I'm hanging up this, if the formation changes this, you do all those tests. So then we go to the next slide. The next one. So awareness, low ROP compared to offset 30% reduction in the ROP. We should have been doing about 120 to 150. We're doing 30, 40-ish, 50-ish. Okay, identification. Possible causes must be defined for analysis. Formation change, one, PDM failure. It could have been a PDM failure, or the started with the run. Then the validation, we went through checking everything else after the run, because during the run, we couldn't see what happened. So after the run, when we did that, going back to the geologist and saying, hey, could you help me here? I think that we balled up. He said, oh yeah, we went through a clay zone that we've never seen before. And I said, so why wasn't that risk identified or thought about earlier? But that was what happened. Okay, so in a way, it wasn't where, because the bit we had just drilled out and started to drill ahead. We had drilled less than 200 feet, and therefore there's no way the bit could have been worn. That's how you eliminate the trend. And also, if it was wearing and we backed off weight, the ROP goes down more if you are wearing as a result. So you check what I call the validation process of, if I'm wearing, this is what I will see. Because if I'm wearing and I increase the weight, ROP will go up minimally or stay flat. But if I drop the weight, it goes down more if I'm wearing. So all these checks were in the data, and in the end, the guys found that out, went back in the hole, not on that same section, on the next one, and it was different because we went back in with a different bit because we didn't know what it was. But in the end, the confirmation was that we've gone through a zone that we had never seen before. Because if we had known, it would have been the preparations for that would have been a little bit different from the holistic standpoint. David, next slide. So in conclusion, I'm not going to read it so we can have some time for questions, but it's just saying that the holistic approach to reducing operational costs is more effective than the way of just trying to maximize ROP every time. And ROP is a condition, is one of the factors for cycle time reduction. It's not the dominant factor. It depends on the project. At the same time, benchmarking must always normalize input parameters to see what is happening. Then you come to the fact that certain aspects as to the physics around the things we do, how we wear, the effect of features and stuff needs to be understood from a holistic standpoint. Yes, it's good to know, but also, there are things that other people have done that is very helpful. I always go back, Sinus work, Fort Brett. I mean, the concept of the perfect well was basically developed by Fort Brett, and it's also one of those good things that we should be learning and applying that fell by the roadside. But the holistic side to solving these problems and stuff, the results, are there, and we cannot be doing, plotting graphs and seeing which one drove faster and going back to do the same. And BHA design is very, very critical to all these conversations. Sometimes, you can make the BHA do stuff for you and not always thinking of BHA that can allow us to pack more weight. And also, we shouldn't be driven by the passion to pack more weight to drill faster. We can drill faster by being more efficient, and efficient means doing more with less. So that's about ending my presentation with time for questions. Yeah. I'm going to go join David for the beer. It's time for beer now.
All right. Yes. I believe I unmuted. All right, guys. So I know we've already got at least one question that's come in so far. I'm going to apologize now for the screen not flipping. On our side, the way that we see it, everything's been flipped and mirrored the way that it's supposed to. But it didn't broadcast through to LinkedIn like it should. So you're coming back to redo all of this.
Okay, no problem.
So we're gonna do everything a second time, and on the second go around, we'll make sure that all of the screen flips and everything. We tried it on a different software, and hey, if we're not trying things, we're not pushing the envelope. And everybody knows I'm gonna take a lot of risk with it. So if you guys have got some questions, now's the time to be able to start firing them off. I know we've got one question here. It's a fairly long one. If you click on that one, yeah, that one right there. Yeah.
Can you read? You get very good eyes. I can read.
I mean, if not, I can always scoot forward and be able to read it. To truly improve drilling, or actually questions. Oh,
is that it?
Okay. Is that the right one? I mean, you can put it on anyone and just you keep switching them. Okay. Question, dear Graham, thank you very much for excellent. Graham didn't say ROP is not important. Graham summarizes it by saying truly improve drilling efficiency. ROP is only one among many performance qualifiers. True. I have a question. In the Bakken, wells are drilled completed in a few days, 7 to 10 days, with ROPs reaching 500 foot an hour. How? And how the holes must have time are engaged, and how much time are the holes engaged? Most of the research in drilling optimization is based on either drilling. Oh, it's too long. Okay, ask your question again, but just make it shorter because that was too long. Yeah, I don't see any other questions right there. How are your thoughts so far? What do you think? I mean, we got a pretty good audience that's stuck around watching this thing for quite some time. If you guys have questions, be sure to make them small enough so that we can actually get them all the way onto the screen.
Yeah, so. I think starting from the laying the background and starting from the benchmarking side to how you do that and getting into how you look at the parameters and the difference between just the mere essence of increasing weight to gain an improvement in your ROP without ensuring that you transition from the script to the shear, because that's a requirement Because at the end of the day, you want to drill longer, and you can only drill longer if you are not wearing, and you can only ensure you're not wearing if you are shearing. So that is the key to that conversation around that, and also understanding that the conversation to ensure static failure dominated by wear must be achieved devoid of the dynamic or vibration side of it. And that's why I went through vibration contribution elements at the system level, and then at the culprit we all jump to, which is the bit. That sometimes is not the bit causing it, but that's what we do.
All right, so we've got a question here. Pick one, just click on one. There we go. Question 1. Any validation with machine learning techniques with model you can predict performance?
Yeah, I think that is coming. My take on that is that I know what the approaches we are doing. We're having 2 approaches to machine learning right now: the Frankenstein approach and what I call the quartet approach, or the Frankenstein approach. What does that mean? So the machine cannot establish somebody has to be able to help the machine understand what to look for. Okay, so just putting in data into the machine and letting the machine identify trends, you're going to go back averaging. But if you can look at it and say, hey, this is what I see here, and this is what caused it, and you begin to fix it, it will help. Now, I didn't get into that. I mentioned the concept of fast learning and then fast following. When you are in the fluid state to your improvement, where you are changing stuff, profile of the wells are changing, lengths are changing, hole angles change, and therefore the lengths change, even drilling to the same TVDs. The hole size is changing. When you are in that phase, it's better to be doing that to get to the point where you stabilize. Remember something, there's 2 concepts. One approach wants you to standardize and stabilize, and one is saying you want to improve. When you stabilize, it means you have improved and you want to make it consistent so you can scale up. And the machine learning is going to be unbelievable there. But I have this itch that we are trying to force machine learning into the realm or the zone where we are trying to improve by reduction. So you have to reduce and then consistent. And if I'm in the consistent range, I can definitely make the machine do everything for me, because I've done the physics and the interpretation, all that side in the reduction. That's it's coming, but we got to do it quicker. We got to do it. We got to do it quicker and put more effort to it. Yeah.
All right. So what is the correct way to drill off to obtain shear cutting ROP with less wear?
Okay. All right. So one thing I didn't talk about also to the drill off test, there's now a process through the holistic emphasis on RPM biased drill off and weight on bit biased drill off. You know how in drill off we keep one constant and then we increase the other one to see. I'm not a believer in I think there were 2 types. One was this where you pile out the weight and let the drill off to find what weight was better. I don't believe that one, because you put the pipe with the string into a condition that you don't. I like the one where you are increasing the weight and seeing what is going on. Okay. Now, you have to know the rock, the lithology. If you are in sandstone, okay, or limestone that is hard, you have to do a weight biased drill off. If you are in shale, you do an RPM biased drill off. Those 2 are very different, and maybe sometime I can get into that, David, at the right time, but I didn't touch on that. But to answer your question directly, you will see like daylight when you get into shear, because the increase in weight and the corresponding ROP increase deviates from the trend established by the K1 value. You see it. In fact, if he wants to see more data and he has field data and he says it to me in the same one, I'll show him where it's at. It's there. And in the lab, it's so clear. You run 5,000 pounds weight, you get 5 foot an hour. 10,000 pounds weight, you get 10, and then you get 10. You go to 20, and you are 40. You've transitioned, clear as daylight. And so there's no, when you see that, and then you say, well, but do I have to be at 40? No, you don't have to be. If you can, so if I did this, and then I did that on the slopes, right? I can bring them, plot them to me. Then I'll know where my transition is at. So I can know where to stay within, So I stay in the shear mode. But if you come down to the script, and that's a mistake we make. We believe that when we add more cutters and more blades, we are making the bit durable. No, you are giving them longevity. You are not making them durable. You are giving them longevity. Total different conversation. That's why I had a point on the slide talking about the differences and relationships between failure, durability, and longevity. But I didn't go there because I didn't want to do 2 hours like Teodoro. Then you're going to laugh at me every day.
All right. What do you mean? Do you mean what used to be called 10-spot drill off test?
10 spot. I don't know what is that.
I mean,
yeah, I don't know.
You've been in this game a lot longer than I have.
Yeah.
Question 2. From your experience, which is the part of drilling cycle with more room for optimization?
The cycle time improvement with more room for optimization. Oh, I think the place where I see us just glance over without really putting the effort in is in our look back. So to really get to the cycle time improvement, you have to understand and do a really good look back. And a look back should not be a collection or tabulation of what has happened in the past. It should be, what have I seen? Why did I see it? Did I expect it? Why did I see it? Why didn't I? So when you have that done, I believe you are 70% there. You have to do things that you know will bring you value, knowing what the value is, so you can measure. And that comes in your look back. So I tend to use the word actionable look back. Very different from the look back where, I tell people all the time, when you give me a look back report, that is just a tabulation or a summary of what has happened. I knew that. I was following the well. I was looking at the daily drilling reports every day. Tell me what happened, why it happened, and did we expect it? And if we expected it, what did we do in anticipation? And if we did not, why? It is not finger pointing because we want to do better. And a look back, to me, is the beginning of the journey. You don't do look backs and you just summarize reports and plot Excel sheets and this one drill first. I don't see how you're going to improve. You're doing what I call the optimization the usual way. It's not. And the sad, I have a very good friend, one of my, him and I, we are talking, you think that it's very passionate, Bill Calhoun. He taught me a lot. The concept I thought about information drillability and what it led to was really driven by Bill Calhoun. And Bill Calhoun, basically, in a conversation way back 20 some years ago, and he was looking at wells that were drilling differently, trying to tie that to the rock and the differences in the rock and what it meant. So there was another guy that also helped me, a guy called Harvey Goodman. I went to him and he said, then he started talking. So there are people that you talk to in isolation that have strong inputs to what you are trying to do. And you need to be talking to all those people. No. And that's how you build your fortress.
All right. I know we're getting a bunch of questions in here. We're trying to.
Hey, I got all day. I'm not leaving.
Oh yeah, you got all day. Okay. Is there any suggestions for optimizations, or explanation to try to avoid flat wear cutters in abrasive formations?
To avoid? Yes. Oh yeah. Yeah. Actually, it's funny. And again, that's one of the things I didn't get into because you easily digress. Remember the paper that I referenced, SP 39306 by Sino? Please read up, check that paper. Sino said that the industry's claim and fear of RPM being the driver of wear is not true. Sino said this in 1994, 19 something. That position that Sino held and validated through testing at the Catoosa test rig is true. At Catoosa, there was a conversation. I'm going to. I want to stay on focus. Okay, so basically, yes, you can design a system from your bait, BHA, and everything else to minimize wear. It's done constantly. And if you hit me up, I'll hit you up too. No problem.
All right.
Yeah, it's a long conversation, but read 39306.
Hold on. I want to go back to Fahud had a question. He was asking about how fast we're drilling in the Bakken and how are we cleaning the hole with 500 foot an hour. Yeah, I think that one maybe. Question: how are we drilling in the Bakken 500 foot per hour and still nicely completing the well in a week or so? And he had also had another question up in there that said, you know, as far as like hole cleaning, like how are we drilling so fast and cleaning the hole?
Okay, so basically, I'll stay straight to I know Ford very well. So the
Yeah,
Bakken,
is that one?
Yeah,
click that one.
Which one?
So where is hole cleaning efficiency in the holistic approach? So he's got kind of two questions. So he's stacking them up here for you.
Well, you make a very good point. Trip load analysis and hole analysis is very, very critical. In the holistic approach, it is key, and that is why I said earlier, you don't go into this what I call a chain solution where let me do this, and if I do this, I go do this. Let me go drill first. Then if I get stuck, I can clean the hole and I go clean it. No. Sit back and realize how fast you can drill and how fast you want to drill, and then measure its feasibility and likelihood at the same time, knowing the potential limitations or challenges it's going to present. And if you can do that with the right drilling system, right hydraulics back and forth, then you do that. But don't do something because you want to do that. Do something because you can do it, and you know the impact of that on your performance and execution. So what you are saying is part of the holistic approach. At the very beginning, there is an understanding that we want to do this. You know, he's talking about 500 foot an hour. If you go to Thailand, they do 800 feet an hour, 1,000 foot an hour. So those guys have done it to perfection. They have filled all the little gaps and crossed all the T's, dotted all the I's, and they are where they are, and they can do that. But I'm not going to say, oh, I saw the ball can do that, so I can do that in the Eagle Ford. No. It's a whole learning, and ball can do a lot of different things that the other unconventionals are not able to do or cannot do. It's a different application. And in fact, I had a slide of applications which didn't come up. I had a slide where I talked about risk in drilling all being applications based. So in a way, it's sometimes you get to the point where you can do what you are just saying for and then you just do it. Yeah.
All right. I want to go back to Peach's question. I know Peach holds. Oh, we're going way too far. Scroll down a little bit. Keep going. Oh. Have you requested any of the applications engineers for the bits you have been running to model when the specific bits transition from scraping to shearing?
I mean, to model, to scraping for shapes, to model it. Yeah, I mean, if you look at, I don't have that sheet back and forth. Yeah, I mean, when I'm working with bit vendors as part of the drilling system design, I ask questions, and I've been accused of asking too many questions.
What?
Yeah. There are people that believe that but that's like you said. You are doing your intro. I'm taking notes. I take notes, and I learned that from a guy called Martin Fear with BP. When I was a young guy, and I used to deal with him I was on the service side. He was at the operator side. Everything you said, Martin Fear wrote down. And you cannot tell him two things about if you tell him A, and tomorrow he asks you something else, you have to explain that or tell him that, oh, I said A, but now I know it's B. But you can't just go there and start spinning yourself. You can do that. And there are, I mentioned Martin Fear, I can mention Alan Sino, I can mention Bill Calhoun. These are people that taught me the right thing the hard way. You have to understand before you engage. You can't just go there and engage because you are 6 feet 8 inches and people should. No. You got to engage the right way.
Okay, so back to Peach's question. Have you gotten them to model that?
Yeah. The parameters I get for what I want to do, the interpretation of scraping shear is in the data. And if Pete wants to find out, I can show him some on bits right now. It's very easily. Yeah.
All right. I know we were getting like
but Pete, also remember something though. That modeling means I need to know the hardness of the rock. So the modeling that they will do will just be a correlated analysis between two different bits or something. So it will not be say this will transition here to there, but we'll say this compared to that, this is what the trend looks like. And I have to interpret what that is going to mean. Okay. There's a conversation again at the same thing that I'm going to just in answering the question. There's a big difference between aggressiveness and efficiency. The scrape shear conversation is talking about efficiency and not aggressiveness. Okay, so again, that's another topic that I'm in trying to stay on course and not be given a crown for the longest presentation. I zoom through quickly, but that is also part of that. But yeah, if you want to see that, and there's nothing better than validating claims or assertions in the field. When I'm in the field running, Pete, is very easy to see. Much easier to see than in fact, there's a paper. I can send him a paper where the modeling was done and we went to the lab, and you could see that if he gives me his email or something, I'll send him. I've forgotten the number. I could have told him the paper to go check that and see.
All right, so we got one more question here. Question to Graham. Obviously, it's not to me. Somebody's asking me any questions. What is the measure of holistic optimization approach benefit? How would you measure improvement in your experience? What are clients' benefits of these efforts?
Reduced a guarantee and consistency in operational cost reduction. That's a measure. A guarantee in the reduction in cost based on cycle time reduction. That's why I remember I asked a question earlier that no matter what process you deploy, the main question, we are not doing this because we are smart people and we have the time to do it. We are doing that because we want to reduce drilling costs. A person I used to work for one time called David Payne told me, he says, Graham, be happy but never satisfied. No matter what you're doing, there's always room for improvement. And by the way, before you get happy and start thinking that you've done something good, show me how our wells are being drilled for free. That's what David Payne told me. Show me how our wells are being drilled for free. So long as we spend money on these wells, find a way to improve our cost reduction. So if you ask me, the drilling optimization approach, which I thought about that focuses on ROP maximization, does not guarantee. Go back to Faouz's question. If I load the hole, can't come out, can't trip, and I spend 1 week doing that, all goes against my cost. But if I bring in the potential to overload the hole as part of what could cause it, I've not mentioned a guy that I learned from also, Larry Wolfson. That's another whole thing altogether. Larry Wolfson was the very person that taught me how to drill slow to drill fast. He says, for these wells, we are not going to go and blow and do 500 feet an hour, because every time we do that, cleaning the hole to come out takes us days and weeks. We got to manage how fast we are drilling and get our cycle time down. I learned that from Larry Wolfson for BP in Alaska. And there's a paper, I've forgotten whether it's SP 50557. You can look at that. Or I can even come back and really send that to you if you want to look at it. So the measure is cost reduction. When Larry Wolfson decided to drill slow to drill fast, look at the cycle time and cost savings. Unbelievable. One of my biggest pains in this effort is when I hear ERD people talking about how fast they can drill. They're talking about, and somebody, when they try to discuss their improvement or contributions to project success and cost reduction through MSC minimization, which I showed the same as ROP maximization, I get a pinch at the nerve, because they are the last people to make that claim, knowing exactly what Faouz just said. But then somebody told me when I called him on the side and said, I would have thought that you'd be the last guy to say this because of what you do. You know what he told me? Graham, if I don't go to my customer and talk about how I can make them drill fast, they don't think I'm bringing value. I said, wait a minute. So we have taught our customers that the only way to improve is to drill fast. They are in charge of the budget and cost, but there's not been a tie to the potential implications from Faouz's question on what that could mean. We need to step back and tell people not what they want to hear, but what they need to hear. And if I can bring your costs down, I can drill fast to do that, like you're doing in the Balkan. They drill very fast in the Balkan because they can. They've done it. They've gone through the cycles. They drill 6.5, 6 inch or something in the lateral, and their flow rates are boom. So and they don't run RSS too. They run PDMs too. And so there's a whole lot of system contribution to what they do in the Balkan. So it's different. But to answer your question directly, the way you measure the holistic approach is your cycle time reduction, which is a direct indication on your cost reduction.
Wow. All right, guys. There's like a ton more questions. So here's what we're gonna have to do. We're gonna have to have Graham come back.
Wait a minute. Okay. Where are you going? Give me one more question. Man.
All right, we'll give you another
Tracy,
one.
why is he trying to drag me out? I'm not going anywhere.
All right,
I'm not...
Oscar. What are your thoughts on the most recent cutter technology improvement the benefit applications are getting by moving to less durable bit designs, masking the cutting structure and design importance for durability?
Oh man, that's one smart guy I used to work with. I know him very well. So what are your thoughts? Well, Oscar, that's a very loaded question. So when you talk of cutter technology, we are in most times trying to relieve the past.
That's the camera. That
what?
Look right at it.
Okay, we are in a way trying to relieve the past without knowing the lessons of the past and how we can make the past better. So there's a lot of the technologies, and I tend to draw a distinction between the cutter itself as a product and the cutter again as a geometry, which is what we're doing a lot of right now. That's a whole. I mean, some are good and some are not, and it's all application driven. And so the question then becomes, when you say that this cutter geometry is not good for this application, people think that you say the cutter geometry is not good. Because I tend to have application conversations. I'm very specific in what I say about certain issues. But people take it like my general position. You see what I'm getting at? Mm-hmm. And it's not because I want a solution. I don't want to generalize. I want to talk about something of relevance to the situation. And if I said this one is not good for this one, somebody will say, oh, I spoke to Graham and he said it's not good. No, that was what Graham said. So I get a lot of those. I mean, one time some guy told me something that was very funny. He called me and he said something and I agreed. He said, oh, I thought you didn't like that. So who said that? He said, oh, that's what I heard. I said, no, that's not what I said. But I wish, David, let's plan a conversation sometime around that. And I think Oscar's question is very, very potent. I don't want to cheat him by. All I say is that Oscar, they're all application driven. And I don't know which ones, by what application, to make any assertion on anything. Yeah.
Oh.
Yeah.
It was.
Read me some more questions.
All right.
I will say I have another live shoot I have to do this afternoon, so some of this equipment has to leave.
Oh. All right. Last question. Okay. Last one.
Two. Okay, two.
No, last one.
Two.
Okay. Which one?
I don't.
Okay, I'll do this one.
All right. Okay. Question number 4. Any cases where one of the output parameters is also an input parameter? Example, torque.
Why? Okay. I make torque an output parameter, not an input, because the main inputs. No, one that could fit the conversation you just had. Your question would be HSI, because HSI is very confusing sometimes, because if I make a claim that HSI as an input helps me drill faster, then somebody gives me data where the HSI is high, but it was driven by the mud weight increase. And I know that the mud weight increase as a component makes me drill slower. So I'm caught between the two. That is where I need to go back to the application. Was I in salt? Was I in sand? Was it depleted? Was it in shale? So the conversation should always be applications driven with the focus and not generalized. So HSI is the one that is very, very challenging to tie down. But torque, I put torque in the output.
You good?
No, I'm not good. I need some more questions.
No. I gotta the kids got to be picked up from camp. I gotta eat lunch and everything else. All right, we're already
one more.
No. We're 6 seconds. We're 5 seconds away from breaking 2 hours.
One question.
No.
Last one.
All right. If you guys want to see more of Graham, if you want to have him back on the show again, like, share, subscribe, tag somebody in the comment section who you think would be able to get something out of this conversation, who you think would get something out of the second time that we have this conversation. Like I said before, I apologize, guys, for the screen not being able to flip. All the tests that we did beforehand showed that everything was working on our side. It's just once it went live, I guess LinkedIn, YouTube, Facebook didn't. I guess we got to go back and watch Facebook. We didn't check that one during the live stream. It didn't. Okay. Apparently the stuff that we were doing, like I said, we test beforehand. It didn't work. So what we're going to do is we will do this one again, because I have no problem getting Graham on the show. He loves being on the show. He loves answering everybody's questions. So next time we'll book out like a 4-hour session, and we'll only let him present for 15 minutes. And then we'll just answer questions for the next 3 hours and 45 minutes. Yes. All right. So with that said, guys, I appreciate everything. Next week up on the show, we've got Jay McGovern. The week after that, we've got a group of students who are designing and building a rig in its architecture type called Tensegrity, which is like using, I can't even explain it. I'll let them explain it. It's going to be a really, really cool show. A week after that, I think I'm on vacation. The week after that, we've got Miles Bolerson from Scout Turbo Drill. In the future, we've also got Mike Shellman coming on from Oily Blog Stuff. Then we'll have Graham come back on the show. We'll probably do this exact same presentation again. Give me about a month to be able to make sure and test and do everything right. And then that way, when he's marking up on the board, everything looks good. And we'll also maybe even have like a second screen. We'll figure out a way to clean the screen faster. I don't know. It's been a 3-year project. I was really excited about it, but we're not going to let it keep us down. Thank you. Appreciate everybody who's been watching. Like I said, share this with your friends. Like us on not on Facebook. I don't care about that one. Like it on YouTube. If you won't go back to YouTube, that's where a lot of the replays are at. I'll try to get all the questions and everything that came through to Graham so that he can be able to go back and answer them. Thank you guys all so much. We really do appreciate it. Graham, thanks for being on the show, man. Let's go have lunch.
Thank you very much.
So, everybody out there watching, as I always say, know your industry.
Flipping.